Today I'm going to explain how to solve the assignment 1, which is about some problems on queuing models. So let's start from the first problem. This problem is as shown here. Some customers are visiting the cell phone repair center at random manner. It is assumed that that arrival occurred according to a Poisson process at the arrival rate of 1.5 per hour. And observation over several months has found that there is some error. This is not shoe, this is a cell phone. Cell phone referral times by the single worker take an average time of 13 minutes with a standard deviation of 20 minutes here. Now we have to find an average number of customers in this repair center for the decision making about how many chairs have to be prepared for all of the customers can sit on it. So we are going to start with several indexes. The first index is our arrival rate. That is 1.5 person per hour. And the service rate we are using this symbol. Mu equal, here is the 13 minutes is half an hour. And this means that 2 persons can be cared per hour. So service rate is 2.0 per hour. And with the standard deviation is 20 minutes, and this can be converted to 1/3 hour. From here, the service time X follows this normal distribution. So the arrival rate is follows a Poisson distribution, and service time is following the general distribution. So this model is M, G, and 1 because there is only one shop. And the thing that we have to find is the number of chairs. So we have to find we have to find length. It means that the length of the waiting customers, and that is noticed as the L, or this can be written as WIP. So in this assignment, I'm going to follow a notation of a queuing model. So I'll use the terms L, And this L is already prepared in table of MG1. Let's see that one. You don't need to memorize this table because this is very complex form, but only needed to just use. So in this table, we are going to use this formula. So let's copy that formula here. L equal rho plus 2L 1 minus rho square and 1 plus deviation square and rho square. Now, only thing that we have to do is calculate this formula. And before calculation, we have to find some parameter. Rho is utilization. So this is defined as like this. No, it's reciprocal. Lambda over mu. And also, we have to insert the standard deviation sigma. So utilization is calculated as the lambda is the 1.5 and the service rate mu is 2.0. So it becomes the 3/4. So from here we can calculate, we can insert here, 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 and here. And about the standard deviation, we have to insert this number to here. So now this is just a simple calculation, and through the calculation, the number came 2.375. So it means that the average number in the system means the cell phone repair center has a number of 2.375 person. So one person cannot be splitted. So this means that 3 persons in average and long term, it means the long term average. So from here, we can deduce that the required number of chair becomes 3. So it is very simple example, but there can be the other kinds of approach. Other approach is to use the Klingman formula or correction factor. So do you remember this formula? CTQ is like this. If we can know this value, then we can calculate the CT by adding the effective time. Also, by use of this cycle time, we can calculate the WIP by multiplying the throughput. But here, this throughput is very same with the arrival rate here. Okay. So in order to use this Klingman formula, we can insert the CA square. It means the variability coefficient is 1 because the arrival rate follows an Poisson distribution. And the utilization U is very same with the law in our calculation here. And TE is the reciprocal number of the where is it? Service rate. Service rate means that 2. So effective time, effective average time is 0.5. So by inserting these values here, here, and here, and there is one more parameter that is CE, and CE is the sigma over TE, and we already know this value. TE is 0.5, and standard deviation is 1/3. So, or we can also know this value. And the arrival rate is very same with the lambda. Okay. By inserting these values to the original equation about CTQ, we can calculate the WIP, and the result became very same with our calculation with this. So after this class, please calculate by yourself about this problem. Okay? Can you follow me, everybody? So let's go to the problem 2. And problem 2, this is problem 2. The service rate of a certain store has a service rate of 10 per hour with exponential distribution. So please analyze and visualize how WIP and cycle time are varying as the arrival rate lambda increase from 5 to 8.64 by increments of 20%, and then to 10. Lambda, the arrival rate became 10. And the arrival rate also assumed as a Poisson process. So this is the first problem. So this store has a service rate mu is 10 per hour with the exponential distribution, and arrival rate lambda is varying from 5, 6, 7.2, and 8.64, and 10. Also, this follows an Poisson distribution. So this is the very simple MM1 model. So the WIPL equal to rho over 1 minus rho, and cycle time W equal mu 1 minus rho over 1. This is coming from the here. This one and this one. We are using these two formula in this problem. So we need to calculate first the utilization rho is lambda over mu. So let's draw some lines. Let's insert lambda here. So 5, 6, 7.2834. With respect to each lambda, we have to calculate rho. It's a very simple one because from here, this formula, this is became 0.5, 0.6, 0.72, and 0.864. From here, we have to calculate the cycle time and the waiting length here. So it's not complex. It's very simple. It requires very simple calculation. So I just put here the answer. Or this is the unit is hour. Some students have calculated this problem with the minutes unit, but it's okay. But in this problem, I will use the hour units. And about the Q length, L became 1.5 to 6.35. So do not need to explain more about this, but we have to see what happens when lambda is 10. If the lambda is 10, the utilization becomes 1. And you can see here in these two formula, if the rho utilization becomes 1, then this the length of the waiting queue and the waiting time is exploded to infinite number. Wait a moment, we be smaller. Let's draw some lines here. First, let's plot the Q length here. Q length is 1, 1.5 to about here, and 1, 2, 3, 4, 5, 6, 7 about here. So when lambda is 5, okay, not like this. We put the number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. So when the lambda is 5, the Q length is 1. So first point is plotted here, and second point is 6 and 1.5 around here. And when lambda is 7.2 about here, the L is becoming 2.87 around here. And when the lambda is became 8.64 around here, and the Q length is plotted here. So by plotting these lines, we can, how about the 0? When lambda is 0, then Q length is also 0. So starting from here, it's here. So there is some divergence. We can think that this line will be converged to this line. And at lambda equal 10, this line will be stretched to the infinite. Also, you can plot the W. If this line is L, we can draw the other line W. And anyway, if we plot the location of each point with respect to the cycle time W, we can find that line also stretched to the infinite at lambda equal 10. Okay, then we need to this problem also can be calculated with the other approach. It means that instead of calculating the W, this can be replaced by the CT equal TE over 1 minus U. Do you remember that from this formula is coming from the deduction process of the exponential process, connected process. I think that all of you can remember this. Also, the Q length, it means that this L can be replaced by WIP. And this is calculated from this formula. And in this problem, the slope is very same with the arrival rate lambda. We have used the RA instead of lambda in previous lecture. So this approach is also possible for this problem. Mr. Watt has solved all the problem with this approach. And second problem, this second sub-problem is not one that I have intended, because my intention is to find some break-even point between the two applicants, but this problem is not like that. This is very simple. There is no need to use the queuing theory. So it means that if we calculate the applicants, this is the one. If the lambda equal 10 per hour and applicants 1 has the service rate is 11 per hour, and second applicants have a service rate of 12 person per hour. And the wage of the applicants 1 is the $400 per week, and wage of second applicant is the $408 per week. And in this problem, week is 5 days and 8 hours per day. So week means the 40 hours. So about the applicants 1, there can be the plus factor and minus factor. Plus factor is the satisfaction. So if we apply the 1 hour, then there may be 10 persons, and with respect to each person, there arise the satisfaction cost, that is plus. That is the 1. And minus is belonging to the wage. So $400 is equal to, per week is equal to the $10 per hour. So this is plus and this is minus. And with respect to the applicants 2, here the same person, arriving person, and satisfaction cost is 125 minus the per hour wage is $12 per hour. So this is becoming 0, and this is becoming the 0.5 bucks per hour. So as shown here, there do not need to use the queuing theory. So this is my mistake, but in my brief scoring, most students have solved like this. So anyway, this was not my intention. Okay. Now let's skip to the problem 3. Problem 3 is 3 o'clock problem. So we have to this problem is like this. There is 3 clocks of the 24-hour market has the working performance with the service rate is 3/2 per minute. And in this market, the arrival rate of the customer is 2 person per minute. And for the simplification of the calculation, let's assume the arrival of the customer and the clock service as the Poisson process. And problem is to find cycle time and the length of the queue, waiting queue, and the entire system. Here, even though the problem asserted that for the simplification of the calculation, however, this calculation is not so simple because the formula that we have to use formulas are a little bit complex. So let's see what is happening in this problem. So arrival rate is 3/2 person per hour. No, arrival rate is 2 per minute. And service rate is 1.5 per minute. And there is a 3 server. So the notation C have to be 3 in this problem. So this problem is C. So we have to use the MMC model. It's this one. So if we see this formula here, we need to calculate the L, WQ, and WQ. And in order to calculate this 4 value here, we need to calculate the probability of there is no people are in the system. Also, we have to calculate this part. This part means that in the long-term perspective, the probability of the over than the number of C peoples are staying in the system in average. So these two formula is a little bit complex. So let's draw the line, draw that before the calculation, first we need to calculate the utilization first. So here we insert the number of server here. So rho becomes the like this, 2 multiplication 1.5 is becoming the 4/9. And first, we need to calculate the P0 and P3. P0 is very complex forms. This is the whole formula. So we need to insert each value to C is 3, so here is written. So I have calculated this formula and by using the Excel, and this becomes 254. And after this, we need to calculate the P. Here, infinite means the time. And implicitly, this means that the long-term average. And this has to be over than 3 in this problem. So the original formula is like this. Here P0 is coming from here. And when you calculate this form, it becomes 181. And in this calculation, all of you have to be very careful in the effective digit. If the effective digit number is being different by term, the final calculation may be affected by this. So it would be better to continuously use 2-digit or 3-digit in this calculation. In my case, I have used 3 effective. So we have calculated this P0 and P over the custom number is over 3. Then remaining calculation is not so complex. The length of over length is like this, 0 plus and now insert the each value. And when you calculate this simple calculation, no, it's wrong, not this. This number is, it's right. What am I doing here? So this becomes 1.478. And from this calculation, do you remember here? The W is like this. So just put this value to here. What is the lambda is 2. And this becomes 0739. And the waiting time in the queue is W minus TE. Actually, this is TE, but in this term, it became 1 over mu. Finally, the length of the waiting queue is L minus rho amid process 1.45. This is the exact values that you have to put into each problem. Some students are a little bit different because not because you are calculated in different way, but because of the digit number of effective. So please be very careful when you calculate these kinds of the problem. Okay. In this problem can be also with the other approach, but I did not find why this calculation is a little bit different from this way. So anyway, let's see how this can be calculated by use of the Klingman formula, applied Klingman formula. Do you remember the CTQ of the MM3 model was like this? This is the Klingman, not Klingman, who have developed. Anyway, this is coming from the factory physics book. So we can use this formula in this problem also. So TE is the 1 over mu. So this becomes the 2 over 3 minutes in this formula. And TA is 1 over lambda. So it becomes 1 over 2. And also utilization is very same with rho. This can be calculated like this. Here RA is very same with lambda, and TE is like this, and M is same with the C, 3. So this result is same with the calculation of the rho on upper side. So we just put the number and by using the Excel spreadsheet, this becomes like this. But it's very occurred that because our calculation was in here, CTQ is this one, this point. So it is a little bit different. So I have to survey why this is different, but it's very close also. So let's see the other indexes in this problem. If we calculate the CT by adding the TE, becomes the 0.735, but it was 0.739. And WIPQ is CT multiplied by RA. Here RA is the same as lambda, so it becomes the WIPQ becomes 0.1636, and it was 0.145. And final index WIP is CT multiplied by also RA becomes 1.470, but also it was like this. So it's a little bit different. So I did not steer the why these two approaches are different. So I will let you know after I find the way to the what is different aspect of these two approaches. I think that this starting number can be wrong, but this was calculated by use of the spreadsheet. So there is two possibilities. One is that there is some mistake in calculation of this value, or these two approaches can be fundamentally different because this formula, do you remember this formula is not the analytic one. It was deduced by some researcher in the academic paper. So there means that in this formula, there can be some gap comparing with the queuing theory. Anyway, this approach also possible to get some numbers. These numbers are also very close to the analytic solution. Okay, let's go to the problem 4. There is not much time remains. The problem 4 is just replace the distribution of service time as the normal distribution. So that problem is this one. So in order to calculate this problem, there can be also two possible ways. One is to use the analytic, because this means that this model is three or MG3. It means that we can use these formulas in order to calculate each values here. Okay, compared to this one, a little bit. This, why is it those two the same? There is only one approach, because this is coming from MMC, and in our textbook we use this correction factor. We have guided to use this correction factor. So in this problem, it is also applied. It means that the correction factor is like this in the book of factory physics. So by multiplying these values to the queuing cycle time and queuing WIP, so it means that the LQ of this model can be like this, and also WQ can be calculated so we need to know what is CA and CE. CA is 1 because the arrival rate is not changed. It still follows the Poisson process, but CE is a little bit different because CE is the T sigma over T. In this problem, the T is, what is sigma? Sigma is 1 over 2 minutes, and time is 2 over 3. So this square becomes 9 over 16. Just put these numbers here and here. And we are borrowing these two values to here. Like this. By use of this relation, we can calculate the RQ and WQ in this problem of the normal distribution service time. And also, the L is calculated by summing this one. And W can be calculated by summing the 1 over mu. And this one is coming from from here, this relation. So I would not calculate the term by term, but most students have calculated in successful way by using this correction factor. So please remember that when converting the MMC model to MGC model, then we have to calculate, you have to calculate the each index based on MMC. And by using these reduced indices, you can use the correction factor with respect to each index of the MGC model. Okay, this is the final answer for the problem 4. And now we are going to number 5. What is time? So 10 minutes are left, so one more problem can be treated. Okay. This is the problem 5. You are an owner of a certain shop. There are 2 workers. They are competing each other for a given job. One worker is named with the name of Abel, and the other worker is Baker. Abel claims that he can work faster than the baker, but Baker is asserting that he can be more consistent, even though the speed is a little bit slower compared to Abel. In this shop, the arrival rate is 2 per hour and following the Poisson distribution. And the statistics of Abel's are an average service time of 24 minutes with a standard deviation, blah, blah, blah. So let's start this problem. The arrival rate lambda is 2 per hour, and this follows Poisson process. And the service rate is a little bit different. There is 2, Abel and Baker. And with respect to Abel, our score is mu1. It's 2.5 hour, and standard deviation is 1/3. And Baker's service rate is 2.4 hour, and standard deviation is 1/30. Because this is coming from 20 minutes, and this is coming from 2 minutes. And 2.5 hour is coming from the 24 minutes. Where is it? Over 16. The reciprocal number of this, and 25 reciprocal number. Okay. So anyway, this is these models are M, G, and 1. Okay, so if we see the MG1 parameter here, we just need to calculate the LQ here, because the criterion for the hiring is number of waiting customers. So we just need to calculate this term here. So let's start the case of Abel. Abel's role is, and is the same for both people. Is 0.8, and LQ1 of Abel is original formula is like this. So we just put the number and calculation result is becomes 2.711. And with respect to Baker, in the very same way, root 2 is becomes 0.33, becomes 2.49. So as a result, LQ2 is smaller than LQ1. It means that the waiting person in the shop can be minimized when the baker is working. So if I am the owner of this shop, I will hire the work baker. Okay. This problem also can be treated as a different way. It means that if we see this problem as WIP, finding a WIPQ, WIPQ is CTQ multiplied by throughput. But in this problem, this throughput is always the same with the arrival rate. So if we are calculating this value, meaning the problem of calculating WIPQ is the same with the calculating CTQ. And this is the MG1 model. So we can use the CTQ by use of correction factor, a very famous formula, and inserting the calculated law, and here is inserted as 1 over mu. And arrival process is 1, and CE is sigma T. So you can insert the number of both workers here. So you can use this Klingman formula instead of this one. But where with the case of this problem 4, problem 3, the final calculation result can be different a little bit with compared to the analytic solution from the queuing theory. But in this problem, it's a little bit more safe because it's not calculate the exact number, but the problem is to decide who have to be hired. So we can use this Klingman formula very safely in this problem.